Okay, lesson 17, the pseudo-steady state approximation. So we are now switching over. We've been doing material balances for a long time for most of the class. Now we're going to examine the rate laws. We looked at elementary. Now we're going to look at some cases when we have non-elementary reactions using the pseudo-steady state approximation. So we're moving from the macro scale of material balances in the reactor, and now we're going to the molecular level to understand a little bit better how reaction rates and rate laws are sort of derived and figured out. So we need to recognize that some written reactions are really a combination of reactions of multiple steps going on. And we're going to recognize what makes a species likely to be a pseudo-steady state species and what that even means. And then we're going to use the pseudo-steady state approximation to predict concentrations of the minor species and use the pseudo-steady state approximation to write rate laws in terms of major species. So for an elementary reaction, it needs to proceed in a single step on the molecular level, exactly as written. And so if I have hydrogen, that means I'm going to have two hydrogens plus two oxygens going to two H2Os. And I have to write it that way because I can't have a 1/2 oxygen at the molecular level. Either I have two oxygens bonded together participating, or I can't just make a half a molecule. And so no fractional molecules. And so this is very unlikely to be an elementary reaction because it requires three different molecules to collide all at the same time with the right amount of energy to form two waters. Typically, elementary reactions only involve one or two molecules. So this example I gave here is not a good candidate for a potential elementary reaction. And only one or two, maybe three bonds are broken or formed. Here we'd have to have two bonds broken. But then we're also forming two more. So four total in terms of bonds broken or formed. Most reactions consist of a sequence of multiple elementary steps. And so it's pretty rare that what you see written down is actually an elementary reaction. So to help you sort of understand the concept of what a pseudo-steady state, I'm going to go through this riddle of the abundance of thorium-232 on Earth. So if you look at the natural abundance of uranium isotopes, we have a bunch of uranium. We have a uranium-238. We have a lot of that. Almost all of it is uranium-238. We have a little bit of 235 and then a tiny bit of 234. But almost all of the thorium on Earth is thorium-232, but its parent nuclide is 236. So why do we have so much thorium-232 and not a bunch of thorium-234, which would come from the uranium 238, which we have a lot of. So there's a lot of that around. Why don't we have a lot of thorium-234? But instead, there's almost none. Like I can't even tell you the percentage of 236. It's so tiny on Earth. So why do we have a bunch of thorium-232? So let's take a look at this. We can treat this like the Earth as a batch reactor. We have basically A decaying to B, going to C in these nuclear decay reactions. So what would be, and we have the design equations listed out here. We're going to treat the Earth's volume as constant because it pretty much is. And so VR will be equal to VR naught. And then what is the rate expression for each species? You can pause and write it down here and discuss if you'd like. Okay, RA is going to be equal to negative K CA. RB is going to be equal to, I'll indicate this as K1. And then RB is going to be equal to K1 times by CA. So that's how B is being formed. So we have a positive sign out in front of there, positive 1. It's the product of the decay of A. And then we're going to be losing some B as it accumulates and forms and decays to C. Then we're going to have our C, which is going to be equal to K2 times by CB. It's just being formed. It's not being consumed and decayed into anything else. And so we can plug that in for our A and our B and our C in our design equations here. And so this is what we end up with. We lose the volumes here in these design equations on this slide because the Earth is constant volume. We can pull that out and then cancel out the volume on either side. So we get these simple dc/dt equations. However, we have to solve these all simultaneously because concentration of B is dependent on the concentration of A, and the concentration of C is dependent on the concentration of B. The only one I can solve, well, we can solve this out by hand, and I'm going to show you how. But I'm also going to model it with Python. And so we have our CA initial, which is going to be our C at time 0. And then we're going to have our, since we're dealing with a batch reactor, the time 0 CA is equal to CA naught because in a batch reactor, CA naught is the initial amount. However, in the flow reactor, as we discussed last time, CA naught is the inlet amount. So try and keep that straight. Sorry about that little easy thing to mix up there. Anyway, so if we take a look, and then we're going to say we're starting with no B and no C present. The rate constants we can derive from the half-lives. And so our K is going to be equal to the natural log of 2 over the half-life. So here we have it all listed out for uranium-238 and 236. We have the Ks listed here. And so 238 has a really small K, 10 to the minus 5. 236 and 235 have a little bit faster decay, 10 to the minus 8 and 10 to the minus 8. 234 has pretty fast decay. It's 10.5. 232 has very slow decay, 10 to the minus 5. And 231 has fast decay. So if we look at the ratio of K2 over K1, we have a very large K2 over K1 in the case of uranium-238 and thorium-234. And then we have a very small one for 236 and 232, and then another large one for 235 and 231. And then I use this here for modeling the Earth, the volume and the concentration. So analytical solution by hand. I take the design equation. This one's easy to solve. I separate, I integrate, and I get CA is equal to CA naught, e to the negative K1 times T. For this one, I have to substitute this CA term in here, so it's a function of time. And then you can see it written over here, substituted in. I rearrange so that I have my CB over here, dCB dt. This is one that this is a differential equation I can solve using an integrating factor. If you need a reminder on how to do that, this is a good tutorial here. We also did it on homework number 1, so you can look at the homework number 1 key. There's also some help on Learning Suite under content. And so if I do the integrating factor and solve, I get this expression for CB. And then for dC dt, I substitute this expression for CB into here. And I integrate with respect to time, and I get this expression for C sub C. So using those equations, I can plot these things in Python. And so you can see when I have 238 decaying to 234, again, because I have that really fast, I have a really big K1. My ratio here is listed here. My K2 is much bigger than K1. You can see I don't even see B, which is our thorium, accumulating much. If I zoom in onto it, I see an initial spike and then decay. But notice this is 1 to the minus 12. If I do it for 232, we can see we have quite a bit build up over time. And our K2 over K1 ratio is really small. And then our 235 to 231, we have another large K2. In this main plot on the left, we don't even see the B curve rise at all. But if we zoom in on that, again, this is 10 to the minus 10. And so really small amounts initially accumulated early in Earth's life and then decayed. We're only so. So what did you observe? What trends did you notice about the concentrations of thorium across those different decay schemes? And how does the rate constant of the intermediate product impact the reaction rate of B? All right, so if you thought about that, you'll notice that when K2 over K1 was really large, my CB stayed very, very tiny. So if this is large, then CB is tiny. And this is exactly what's happening with the pseudo steady state approximation, is that we are saying that our CB is so tiny. And because CB is so tiny, the reaction rate of B is going to be very, very small. Small enough that we could even say, let's just set that and say it's approximately 0. Notice we're setting the reaction rate of B equal to 0, not the concentration of B equal to 0. That's important. So, yeah, we just discussed that. So the pseudo steady state approximation is saying just what I explained, that the max concentration of our intermediates is going to be very much smaller than our reactants. And because that concentration is much smaller than our reactants, we can basically say for these intermediate active centers or minor species or pseudo steady state species, all the same thing. We can say that the reaction rate for that is going to be approximately 0 relative to the reaction rates that involve the main reactants, the more stable major reactants. So it has to be an intermediate though, right? It has to be an intermediate, and the concentration has to be very, very small for us to make this assumption. So we're going to try to estimate the concentration of our minor species in terms of the major species. We're going to make it so that when we write the rate laws, only major species will be present, no minor species or active centers or pseudo steady state species allowed. And then what this really does is it reduces computational time and number of rate constants that need to be known. It gives us a good starting point for us to make guesses at what the rate law looks like. It gives us an educated guess, so we aren't testing every single possible combination of functional forms. So it gives us a functional form that we can start off of. All right, so we're going to go through an example for hydrogen bromide formation. Again, we have this hydrogen plus bromine going to 2-HBr. We have 4 steps that we're hypothesizing are happening. Initiation, where the bromine gas gets radicalized to form 2 bromine radicals. Then we have propagation, where a bromine radical reacts with a hydrogen gas and makes HBr plus 1 hydrogen radical. And 1 hydrogen radical plus bromine could also make a HBr and then another, and then a bromine radical. And then to terminate, 2 bromine radicals find each other and form a bromine bond. And so you'll notice with each of these steps, we're only breaking 1 bond and forming another bond. So in step 1, we broke a bond. No other bonds were formed. In step 2, we broke the hydrogen bond and we formed the new HBr bond. So that's just 2. And then same thing with step 3, and then step 4, we only have 1 bond being formed. So this is what I mean. Elementary reactions typically only have 1 or 2 bonds being broken or formed. So how are we going to divide the rate law based off of this proposed mechanism? We are going to have to derive the rate law. So we're going to write all the rate laws for each of these steps. And then we're going to set the rate law for this, not the rate law, but the rate expression for our pseudo steady state species equal to 0. And then we're going to find the concentration of our pseudo steady state species as a function of major species. And we're going to do that 2 different ways. Brute force, we're just doing a bunch of arithmetic. And then we're going to do the add and subtract method, which is a bit more elegant and could save you a lot of time when you're tight on time. I wonder when that would be. And then we take this rate expression and we make our rate expression only a function of major species, which we can measure because they're stable and they stick around. So we can pseudo steady state species are typically short-lived, and so it's very hard to sample it and then have the time to measure it before it disappears. So, all right, we're going to start with the add and subtract method. We have the 4 steps that we hypothesized up above. See if you can write out the rate expression for each 4 of these steps. Pause the video, write out the 4 rate expressions, and once you feel like you got it, unpause and see how it matches up to what I share. Okay, so we are going to have our rate law for step 1 is going to be, I'm going to label this with a K1. So this is K1, K2, K3, K4. So that's going to be only dependent on my bromine concentration because it's irreversible, single directional arrow. And then we're going to have R2, which becomes K2, concentration of my bromine radical, concentration of my hydrogen. And then R3 will be equal to K3, concentration of my hydrogen radical, concentration of my bromine. And then R4, I mean, will be K4, concentration of my bromine radical squared. So we got all the rate laws written out. And so we need to identify what are the pseudo steady state species? What are short-lived, going to react very quickly? Well, that's going to be our radicals, right? So these are our pseudo steady state species. Radicals are short-lived, and they're good candidates for pseudo steady state species. One thing to notice is that these don't show up in the main reaction at all. So they're all intermediates. They all get consumed by the end. And so, okay. Then for the add and subtract method, we're going to write out the rate expression for our pseudo steady state species. So if we go back here, we want to write all rate laws, which we just did. And now we need to get to this part of setting our pseudo steady state species rates equal to 0. So what will the rate expression look for my pseudo steady state species R bromine and R hydrogen? And let's just write it only in terms of the rate laws here. So in terms of R1, R2, and R3. Pause the video for a minute and see if you can write out the rate expressions for the bromine radical and the hydrogen radical in terms of R1, R2, and R3. Okay, let's see how you did. Our bromine radical, it's involved in R1, and there's 2 of them, right? So I'm going to have 2 R1 here. It's also involved in the second reaction, so I'm going to have plus R2 here. And it's also being produced in my third reaction, and I made a mistake here. Just a moment. This should be minus because it's a reactant in that expression. So we do minus, and then in 3, it's a product, so we're making R3 here. Whoops. Okay, so plus R3, and then we have 2 being consumed over here. So we're going to be making, doing minus 2 R4. So now let's do RH radical. That's being produced in, one is being produced in reaction 2. So we're going to have plus R2 here. And then we're going to have it being consumed in R3, so we have minus R3 here. And so we can say that these are pretty much going to be zero because the concentrations will be so low, so their rate of reaction will be really low relative to the other reactions, other species being produced. Okay, so what do you notice here? What can we do to simplify this? Pause and think about that for a couple seconds. Okay, what we notice is that if I add these two together, is if I take and if I add something that's 0 plus 0, that's still going to be 0, right? And if I add this together and I find out that 2R1 minus 2R4 is equal to 0. And so what does that mean? Well, R1 equals R4. Furthermore, we also know from this expression up here that R2 equals R3. Now we've shortcutted a lot of algebra, and so which you'll see later on. So R1 will be K1 C bromine 2 is equal to K4 C bromine radical squared. So I want to get this in terms of the major species because there's no way I can measure that. And so I can say, well, C bromine squared will be equal to, sorry, that's K1. K1 over K4 C bromine. And we can take the square root of that on both sides. And we can get rid. So we took the square root. So there we are. We already have an expression for the concentration of bromine in terms of the major species. So now we need to get what is my hydrogen radical going to be equal to? Well, we also have this relationship of R2 being equal to R3. So if we take a look at that, R2 is equals to R3, that's going to be K2 concentration bromine radical, which we already know in terms of bromine gas, is equal to K3 concentration of hydrogen radical. There it is. That's what we want to find out. Sc bromine. And then that's it. So now we can rearrange this. I'm going to have CH radical being equal to K2 over K3, C concentration of my bromine radical, concentration of my hydrogen, and divided by the concentration of my bromine. Now remember what concentration bromine radical is? Let's see, that's going to be, is it K1 or K4 on top? Okay. So that's going to be equal to the square root of K1 over K4 concentration of bromine. And so I can plug this guy into here. So I'll get concentration of my hydrogen radical is equal to K2, K3. So it's going to be times by the square root of my K1, K4 concentration of bromine and the concentration of my hydrogen. Whew. And this isn't even the brute force method. All right, so we can simplify this a little bit further. K2 over K3 square root of K1 K4, and we'll put the C bromine down here because we have this guy over here. So that's going to cancel out with the partially cancel out the C bromine to the 1/2 power up here. And so we're going to end up with concentration bromine to a negative 1/2. And then we're going to have, and to make sure we know that that ends there. There we go. So we got it. The concentration of our hydrogen radical in terms of the major species. Now, one thing to note is that here I didn't have to multiply by anything to get these things to add up and cancel out. But if necessary, a constant times 0 is 0. So I could times by a -1, a 2, whatever I need to get things to add up and cancel out. So if it doesn't line up quite like this, you can times by, whatever you need to get things to start canceling out to make this method work. Now, if you can't quite see how to cancel things out, you can always fall back to this brute force method. But I'm warning you, it's brutal. So we are going to say brute force method. I'm going to start with my hydrogen radical because it's smaller. So I'm going to say, well, we know RH2 is going to be equal to R2 minus R3. That's going to be equal to my K2 C bromine radical, C hydrogen, and minus my K3 concentration of my bromine gas, concentration of my hydrogen radical. I'm going to say, well, I can set this equal to 0, and now I start solving. And so I'm going to end up with, I'm going to solve for C hydrogen radical, and I'm going to end up with, and you could choose either one, bromine radical or hydrogen radical. I just know from hindsight that this is where I have to get the hydrogen radical based on our previous work here in the class. And so I'm going to say K2 divided by K3 is going to be equal to concentration of hydrogen radical, H2. So basically I added this over to this side, and now I'm rearranging and bringing things over for that. And so I'm going to be also dividing by my concentration of my bromine. And so we saw that earlier, but I still have this in here, so I got to get rid of it. So that's where I have to use my other relationship of, and I'm going to leave space here for me to come back once I have bromine, but my other relationship here is going to be concentration, my bromine radical expression, which we know is 2R1. Let's take a look at that real quick. Minus R2 plus R3 minus 2R4. So we're going to be minusing R2. We're going to be adding R3. We're going to be subtracting 2R4. If I write that expression out, I'm going to have 2K1 C bromine gas. Sorry, not. Whoops. Can't get it to advance now. Come on, buddy. There we go. Finally got it. All right, C bromine minus K2, C bromine, C hydrogen. Man, this is like the most boring part of any lecture I give. I don't know how to do this any more entertainingly. So at least you guys can like do this at double speed or something. And so I'm just writing out all of these rate expressions. And so that's just all that's going on here. And this is brute force method is brutal because it takes a long time. Okay, so I can be here. I can be okay. I've got the C bromine. I know what my C hydrogen is, right? That I have on this previous slide. So I'll plug that in here. So I'll get a K3 times by K2 over K3. And you'll see how if we did the add and subtract method, I wouldn't have to be doing this step at all. Um, because eventually it works out here. So this is all just C hydrogen radical. And then I have my concentration of my bromine, and we see this cancels out here, cancels out there, this cancels out, this cancels out. And so now I just have K2 C bromine, C hydrogen gas, and voila, I have K2 C bromine, C hydrogen gas. So this, all of this whole expression here simplifies down to this expression. So I end up with 2K1 C bromine minus K2 whoops, I don't want to be writing that. I'm going to be writing the expression I just came up with here. So let me erase the rest of that. Oh, goodness. So that's going to be plus my K2 C bromine radical, C hydrogen radical, minus my 2 K4 C bromine. You can see we came to this point a lot faster with the add and subtract method. So now we're just left with this, which is equal to 0. And we can see how if we rearrange this, we're going to end up with, I'm going to write it up here, over here. So I'm going to end up with C bromine. If I solve for this, I get C bromine radical is equal to, oh, sorry, and that's squared. That should be squared there too. Okay, and then C bromine radical is going to be equal to our K4 on K1 over K4 concentration of bromine, like that, as we've seen before. So I have this, and we're not done yet. We got to go back here and substitute it in here. So really the moral of the story is, if you can see a way to do the add and subtract method, try and do that first. You'll save yourself a lot of time and effort. So it's concentration of bromine. So now we have that concentration of hydrogen, 1 over the concentration of bromine, which again, we can simplify this further to what we had back here. Okay. So I don't know what I just did. Anyways, okay. That's a good place to end it then. So the summary here is that non-elementary reaction rates are not a function of stoichiometry. We've been assuming that all along just to simplify the problems for you in this class, but generally speaking, most reaction rates you're going to come are not, or that you're going to see are not elementary. Some species have concentrations much smaller and than the concentration of other species. So you can assume pseudo steady state approximation. And then you can use the pseudo steady state approximation to predict concentrations of the minor species and obtain rate laws in terms of the major species. And so the species are never at, like, species that can't be at pseudo steady state are initial reactants, and species only disappearing or appearing. So if it's only a product or a reactant, not a good candidate for being a pseudo-steady state species. Species possibly at steady state are ones that have slow formation, fast depletion. So radicals are a good candidate for that.